evening, everybody. Welcome back to the fourth lecture in this series. I'd like to introduce you all to Dr. Matthew Large. He completed his undergraduate studies even at Surrey University. He did his PhD also at Surrey University, completing that in 2016. He is now a postdoctoral researcher in the materials group here at Sussex University. So yeah, over to you.
Thank you very much. So yes, that's me. I was going to do a little introductory bit, but I didn't realise I was going to get a formal introduction, which is fantastic. So yes, this is me. I work here at Sussex in the materials physics group, but I also do have a sneaky alter ego on YouTube as Dr. Nano. Some of you may have seen this advertised in the emails and things that have gone out about this talk. But if not, you know, some of the stuff that I'm going to be talking about today is on there if you're interested, and there'll be some other things as well, depending on how well you enjoy the talk today. So, first question we've got to ask is, how small is nano? Because it seems obvious to me, because I do this sort of stuff every day, but I kind of imagine that not everybody's really going to have a feel for how small these systems really are. So, the first thing before we answer that question, and this sub-list of questions grows, is what does nano even mean? So nano is one of the SI prefixes. The SI, the International System of Units, is how scientists communicate quantities to one another. Regardless of what language we're speaking, the SI is always the same. And we have a set of words which we can append to the beginning of the names of our units to tell people how big things are, rather than using really obnoxiously large numbers. I'm going to focus in right in the middle of this today, because I'm not talking about really cosmologically big things or even atomically small things or subatomically small things. But we're kind of start by covering the range of things that normal human experience is relevant to. And the biggest sort of thing that I feel is easy to visualize, if we draw ourselves a nice scale, is kilo, thousands of things. Kilogram, for example, you'll all be familiar with, but as we're going to be talking about length today, let's start with a kilometre. So bonus points for anybody who can name the bridge, but that particular bridge has a centre span of just over a kilometre, a bit less than a kilometre and a half. So that's 1,000 of metres. Next down, we have no prefix, which is the unit itself. So 1 metre is about the length of a full-scale guitar. Next, we keep going smaller, and all of these are separated by factors of 1,000 as well, you'll notice. We have millimetres in particular, about the thickness of a credit card. And now we're going to start getting beyond the realm of what it's easy to perceive with the naked eye, with our hands and bodies, down to the micro level. So these are things where you need to start getting out microscopes for obvious naming reasons. A micrometre is about the size of an individual cell, particularly small cells, around 1 micrometre. A red blood cell, for example, is about 8 micrometres across. And then finally, after all of that, we arrive at my level, nano. So this 10 to the minus 9 means that we're talking about 1/1000th of a metre. And things that are about 1/1000th of a metre across include individual strands of DNA. These in particular are just around 2 nanometers across. So let's put that in perspective, 1/1000th of a meter. What does 1/1000th really look like in any practical sense? Imagine for me, if you will, the Earth in its entirety, our pale blue dot, as Carl Sagan called it. Pretend now that that entire planet is 1 meter across, 1 meter. And what we're going to do is we're going to zoom in and try and find something which is 1 nanometer across. So we're going to zoom in past the United Kingdom, which turns out to be about 10 centimeters long, size of a postcard. We're going to go London to Brighton is about 6 millimeters. Into the university campus, which is 80 microns, a hair's breadth tall, into this building that we're sat in. And within this building, this very lecture theatre. Now, this lecture theatre, on this scale of the Earth being a metre across, is only 1 micron, 1 micrometre. So even this big space is still only 1/1000th of the Earth's diameter. So what then is about 1,000th the size of this room? Turns out it's about the height of a first-class postage stamp. So on the scale of the Earth is a metre, this is a nanometre. And we all are about the size of nanomaterials, 1 to 100 nanometres. So there's an obvious question begged here. How can we possibly find anything that small? Surface top of this table is about 1 square metre. If I had a 1 nanometre piece of material and I dropped it on there, trying to find that again is like trying to find a postage stamp from space. That's not an easy challenge. So the short answer to this question, how can we see anything that small, is literally you can't. Light doesn't let us see things that small. But the more detailed answer in the footnote there is microscopes. We don't have just light at our disposal. So light microscopes, like the one shown here, or like this beautiful example that I was given for my birthday recently from the 1940s, fundamentally the same technology, just a bit older, a bit dustier. This allows us to see objects down to the micrometer scale, down to a millionth of a metre, which is pretty good, but ultimately it's the wavelength of that light which limits us. So what we do, and let's pull up a scale again, because it's always nice to have these scales, and we can put things in perspective. So we'll put our optical microscopes up the top there. This is the sort of the size range that we can see objects with those instruments. And to give you an example of an image from one of those microscopes, here's a material we're going to come back to later, some silver nanowires on a sheet of glass. So the next thing we have are electron microscopes. So electrons, as you may have heard from other talks in this series, or you may know more generally from science communication, do behave like waves under certain circumstances. So that means that we can use them exactly the same way we use light to image the surface of really, really tiny things. And these can see, in inverted commas, because we're not really seeing, we're not using light, objects from about that same millimetre scale all the way down to the nanometre scale. In principle, depending on how you do it, you can actually get down to atomic resolution with electron microscopes. You can see individual atoms. So that puts us here with the electron microscope. And by way of an example, here are some silver nanowires again. But this time, rather than seeing them as these big, hazy, fuzzy, almost like light pipe cleaners, we can actually see their real structure and how physically big they actually are. And right in the middle here is another candidate that we'll come back to talk about in a little bit, is graphene, a graphene sheet. The last type of microscope we have at our disposal, and in my opinion the most powerful, is completely different. It doesn't operate on the same principle at all. These are scanning probe microscopes. These don't see, they feel. The atomic force microscope, or AFM, is one particular breed of these microscopes. And you could also think of the acronym AFM meaning atom feeling machine, because that is really what it does. We put that on that scale, down to the nanometers again, similarly with the electron microscope, down to atoms, if you try really, really hard. Now these work very much for those of us, some people in the audience possibly not old enough to remember, this is a record player in essence. That is all it does. You have a tiny, tiny, very, very sharp needle which runs across the surface of your material and rides up and down on the corrugations of the surface. And we can detect that and build a picture out of that information. So this picture here is the surface of latex paint. This is your Dulux emulsion, other brands available, that you might paint the walls inside your house with. So this is a very common material. These particles are about 200 nanometers across. But as I say, because we're feeling the surface, we're looking at height. So this isn't just a two-dimensional picture, this is three-dimensional information, and this is why I like the AFM so much. It allows us to not only produce an image of what things look like, but we have detailed information on the topography, the shape, the thickness of these materials as well. And to give you an example of just how powerful the AFM is, I mentioned this before, these little squiggly, almost like lightning strikes across this slightly grainy image here from one of my colleagues, Dr. King, are individual strands of DNA. This is what the DNA in our bodies actually looks like on the nanoscale. Excellent. So then, We know what nano is. We have a sort of feel. It's difficult to visualize really what a billionth of a meter looks like, but we've done our best. We have an idea of how we can find these things, so we're heading in the right direction. So what is a nanomaterial? Here's a definition. This is the international standard definition for a nanomaterial. It's anything which has an external dimension in the nanoscale. And I've already mentioned on our Earth is a meter. This is between the postage stamp and us, 1 to 100 nanometers, roughly. But there are multiple different ways a material can have any dimension on that scale. We could have something which is squashed flat, so it's in the nanoscale thick, but otherwise very, very big. So you might call that a sheet or a two-dimensional material, something like graphene, which we'll come back to. Or you can squeeze your material in 2 dimensions and have something which is only nanoscale in 2 directions and very, very long and thin like spaghetti. That would be a 1-dimensional material, or a rod, or a wire, or a nanotube, something like that. Then you can also just squeeze everything down to the nanoscale and you have a so-called 0-dimensional material, a quantum dot. So, with that in mind, we have an idea of what we're looking for on our safari of this world of tiny materials. We have our tools for how we're going to find them. Let's dive in to what nanoscientists jokingly refer to as the flatlands, this world of low-dimensional structures after this novel by a Square, a 2-dimensional author. And let's go and find some things. Now, I thought, back when I was trying to conceive what this how this talk was going to be put together, that it would be terribly remiss of us to go on this journey without a map. So, this is one that I've drawn of our tiny world, which I was up very late and or early, depending on how you look at it, doing last night. So let's pick apart some of these things that we're going to find. We've got graphene. Hopefully, most of you will have heard of graphene. It's been in the news a lot. It's a very, very popular material because of its spectacular properties, which we'll get back to later. We also have its evil twin, if you like, hexagonal boron nitride, which is almost exactly identical to graphene, except it's white rather than black. We have fullerenes. So these are a class of molecules made of tiny cages of carbon atoms. And the first ones were discovered here at Sussex. We have carbon nanotubes, these very, very long, rolled up pipes of graphene in essence, which are very one-dimensional in their nature. And we have transition metal dichalcogenides, as we're called. These are a bizarre family of different materials which have an enormous range of different physical and electronic properties. So this is what we're looking for. So let's start by investigating some of these creatures. First, let's look at graphene, sheets, our 2-dimensional materials. I'm going to use graphene as the archetype, as that's the one that most people have heard of, and it's the one that's had the most research done on it to date. Now, of course, graphene doesn't come in nature in 2-dimensional sheets. It comes stacked up like leaves of paper in a book. Now, this material, its bulk form, if you like, is something that you will all be familiar with. Everybody will have this in their homes somewhere. They will have used it throughout their lives for doing various tasks. It's graphite. So this material, as hopefully you'll also be aware, is the core of all of our pencils. This is pencil lead. The interesting factoid there is that pencil lead was never made of lead. When people first discovered graphite, they misidentified it because they didn't know the chemistry of materials to the degree we do today back then. So they found this very, very soft silvery material and they thought it was the other very, very soft silvery material they'd mined somewhere else. Fair enough. Now, to convince you that your pencils at home contain graphene, if we were to hypothetically strip the wood away and crack that lead so we have a nice clean surface on the end and put it in an electron microscope, what we would find is something like that. Beautiful, beautiful rolled up sheets of graphene, all folded together and packed against one another. So with that in mind, how can we get the graphene out? That seems like an easy enough thing to do, right? So if you think about what this structure actually looks like at an atomic level, what we have are these stacked up planes of tiny hexagonal arrangements of carbon atoms. They're all held together by covalent bonds in the plane, so they're very, very strong. But they're not very strongly held together out of that plane. This is what makes graphene a two-dimensional material. Now, if we took some Scotch tape, we scribble out a big pencil mark, put our Scotch tape down on the top and peel it off, and keep doing that over and over and over again, we can gradually chomp through these layers, and what we'll be left with is a beautiful, perfect monolayer of graphene. Now, if you were to go home and do this back in, say, 2002, and publish your results before 2004, that'd be enough to get you a Nobel Prize. As indeed it did. For our colleagues Konstantin Novozilov and Andrei Geim from the University of Manchester, who I imagine you'll likely have heard of. And they were awarded that 2010 Nobel Prize in Physics for their groundbreaking experiments, particularly focused on this material. This is a figure from their first paper on graphene. And since then, so this is their paper, 2004, the amount of research on graphene that has been published throughout the world has grown by an absolutely staggering degree. Most scientific papers published for all of human history are on graphene and related materials. This is a big area of research at the moment. And you can see that since 2004, up to the year they were awarded their Nobel Prize, we went from basically no papers to somewhere around 6,000. And since then, 10 years after their original discovery, we're at 14,000 publications. And this was 5 years ago, so that number has carried on climbing ever since. And there are a lot of reasons why people are interested in graphene. You may have heard of some of these reasons. So here is our graphene. It can do a lot of things that other materials can't. For example, it's strong. And by strong, I mean really strong. It is essentially the strongest material that we know to exist. It takes more force to break a graphene sheet than if you had an elephant standing on a pencil and that pencil point was pointing down at a graphene sheet. That would not break a monolayer of graphene, in principle. It conducts heat. It's an exceptionally good conductor of heat. Makes it very, very good for lots of things. It's also completely impermeable. No molecules can get through a perfect graphene sheet. The only thing that's known to are individual hydrogen ions, as you might get in dissolved in water, for example, but even that is under very specific conditions. Further, as everybody I would like to believe knows, but maybe that's not quite true, speaking outside my field, I don't know. It's an exceptional conductor of electricity. Again, one of the most that thing materials we know to exist. Electrons in graphene behave like they have no mass. They move like photons of light, ballistically, nothing slowing them down. Graphene is also impeccably transparent. The monolayer is completely invisible to the naked eye. It only absorbs 2.3% of the light shone on it. And it's cheap-ish. And by ish, I mean graphite is very, very cheap. Making graphene is not so much, not yet at least. A lot of the approaches used for making graphene are based on chemical methods, and we'll come across one of these later on when we're looking at a different nanomaterial. But what you can also do is you can make graphene in liquid. There's a relatively famous lecture by a colleague from Trinity College Dublin, available on YouTube, a TED Talk in fact, where he demonstrates producing graphene in a kitchen blender using fairy liquid and pencil shavings. If you perfect that process a little bit more, you develop it somewhat further, you can produce something like that. That is a litre of graphene, which we prepared in our lab. Now obviously, if we do things on this scale, it makes graphene much, much cheaper, much more available, and we can do a lot more with it. And speaking of things we can do with it, let's look at an application. What's graphene useful for? Beyond the sort of, it's quite strong, it's quite conductive, what are the really obscure things that we can do with it, the exciting stuff? So let's talk thermal invisibility. Objects emit light, radiation, electromagnetic radiation, depending on how warm they are. Our absolute temperature, measured in kelvins, is what dictates, essentially, how much radiation we emit and where it's brightest in the electromagnetic spectrum. So human bodies emit light because we are at about 310 degrees above absolute zero in the infrared range. This is how thermal imaging cameras work. They essentially look at how bright something is in that particular wavelength range, and you can assign that to a temperature. Another black body emitter that you'll all be familiar with, of course, is the sun. Now, the surface of the sun is at an absolutely sweltering 5,800 degrees above absolute zero. And that means that not only does it produce an astonishing amount of electromagnetic radiation, but most of it is in the range of the spectrum we can see. This is light. This is where white light on Earth comes from, the sun. This is black body emission. And to go all the way to the other end, I know that this series is Sussex Universe, so let's talk about the deepest reaches of the universe very briefly. Behind all of the stars that we can see is the cosmic microwave background. Now, this spattering of microwave radiation that we can see at all directions in the sky has a black body spectrum, so we can associate a temperature with it. And that temperature is just a shade above 2.7 degrees above absolute zero. This is about the coldest thing I'm aware of that naturally exists anywhere. So what does any of this have to do with graphene? Well, we have to start talking about thermal emissivity. So I said that temperature dictates how much radiation we give off, but it's not just temperature. What our surface looks like has an effect as well. So black surfaces that are very, very rough are very good emitters of thermal radiation. This is where the phrase black body radiation comes from. Conversely, very shiny metallic surfaces are not very good at emitting this thermal radiation. So if we can take graphene and we can switch it between one and the other state, we can tune how much radiation we give off. And so we can make our bodies look like our backgrounds, as it were. So what we would do, and this has been done, published last year, is you produce what is essentially a capacitor. You have a big gold sheet, very, very thin plastic membrane soaked in a salty electrolyte, and you put a sheet of graphene on top. What happens is when you apply a voltage across that cell, the ions from that electrolyte soak into the graphene and they change the number of electrons that exist in there. What that does is change the emissivity. So it makes the graphene go from very black to very slightly silvery. And this means we can go from having something which is almost as warm as we are to something that's thermally invisible. Now, there's lots of applications for this. If you've ever seen an image of a house taken with a thermal imaging camera, you will know that the way that you lose most heat is through your windows, because glass is completely black in the thermal infrared range of the spectrum. So if we could put something like this, but transparent, on our windows, we could keep the heat in winter, and we can let more of it out in the summer, just for the price of putting a few volts across each panel. Now, there are other things we can use this for, but I won't dwell on them. But suffice to say that this would prove immensely inconvenient and very distressing to any extraterrestrials which rely on thermal vision. Let's go to something completely different. Vinaigrette. Anybody? Make this yourself? Oil and water are the two primary constituents. Anybody who's ever tried to mix oil and water will know that it isn't very easy. You can blend oil into water and you'll get these beautiful little spherical droplets. But if you don't add anything to keep those droplets apart, eventually they will all separate and all you'll be left with is a bottle with water on the bottom and oil floating on top. Soap is a very good material for stopping this happening, for keeping these droplets stable. But another thing that you can use, which is some research work that we've done in our group, is you can use graphene for exactly the same thing. Now, from what we know about graphene, it's very, very electrically conductive. So not only have we stabilized that emulsion of oil and water droplets, but we can make it conductive as well. So if we siphon that up into a pipe, for example, and apply some little electrical contacts, we can measure a current through it. And when we did this, what we found is that this system, this material, is immensely sensitive to very, very tiny stretches. In fact, this is the most sensitive way of sensing stretches using a liquid that exists. And that gave us an idea. Maybe we could use this for monitoring things, monitoring bodies. So if you took one of these little sensors and you strapped it around your chest, you'd be able to measure your breathing, measure your heart rate potentially. And the idea that we'd had is that this might be particularly useful for at-risk infants all over the world. This idea gained a bit of pace with the local media, the press, and this is something that we're still looking to develop actively with some external companies as well. So that's graphene. Let's move on. Wires and rods, our one-dimensional materials, and we'll start with carbon nanotubes. Imagine you have a sheet of graphene like this. These tiny little hexagons, which you might not all be able to see, apologies, are printed to our scale of the Earth is 1 meter across. This is what graphene would actually look like if the Earth was a meter long. Each of these tiny hexagons has 2 millimeters along each side, which is 0.142 nanometers, the length of the bonds between carbon atoms. And if we roll that up into a tube, like that, and stitch along the bonds along those two broken edges, what you get is a carbon nanotube. Now, that's not really a practical way of making nanotubes. I can do it with a sheet of paper, but I can't do it with a sheet of graphene. So we grow these, and we grow these in a slightly different way. We use a process known as chemical vapor deposition. This is another way that a lot of people make graphene. So what we do is we take a surface, a substrate, we coat it in tiny metal nanoparticles. We heat it up to 1,000 degrees and then pump in some carbon-containing gas like methane. What happens is the carbon atoms dissolve in those nanoparticles and they produce these ring structures. And so these metal seeds, as they're called, rise up and push out a nanotube underneath them. What happens if you do that is you're left with these beautiful little cakes of carbon nanotubes. But the cool thing about them is if you put one of those in the electron microscope and look at that edge, is what you find are these gorgeous, almost bamboo forest-like structures. Carbon nanotubes all perfectly straight and packed together vertically. Now we can do some things with these, but also they have some interesting properties of their own. Because of this structure, when they're very, very, very aligned in that one direction, light, when it falls on the surface, basically rattles down between these nanotubes. The nanotubes are black. So this means that these absorb almost all incident light that falls on their surface. They are the blackest material in existence. And this is an example from a company that makes this stuff commercially called Vantablack. And you can see these are two identical objects coated with these nanotube forests. And one looks like a statue. The other looks like a hole in reality. That is really how black these materials are. But what else can we use them for? If we take that forest and we peel away an edge, because these nanotubes stick together with such immense force, they actually pull off into like a ribbon. If we take that ribbon and we attach it to a spindle, spin it around really, really fast as we pull, and what we can produce is a fibre, very, very, very thin, very, very, very strong. So here's our nanotube forest, as we have on the side of that image up there. You can see this ribbon of nanotube filaments pulled out, and then we spin it round into these tiny little fibre structures. We can make individual ones, we can ply them up, you can weave them, you can crochet them, you can knit them, whatever you like. Produce all sorts of interesting structures. But what's interesting is how strong they are. So graphene is very strong. If you roll it up into tubes, the tubes are very, very strong. A nice comparison that we can make to a natural material that's very, very similar to this is spider silk. Spider silk is famously stronger than steel per unit weight. And the way that we measure that strength, that toughness, is how much energy it takes to snap a filament of it, divided by how much that filament weighs. So you can see spider silk here breaks at a certain value of that energy, that work done. But these nanotube fibres absorb 4 times as much energy. They're 4 times stronger than spider silk, which itself is stronger than steel. And that's 4 times tougher than spider silk. That's 20 times tougher than Kevlar. This is one of the strongest materials that we can make, that we can physically hold a macroscopic amount of stuff. That's really cool, but we can go even further than that. We can weave up these individual fibres. So there's another example of one. So this is from, again, Dr. King's work. She works in this area on these fibres a bit more than I do. But what we do, we, the royal we, is we can weave those fibres up into a fabric. And this fabric, of course, is very strong. It's electrically conducting. But what we've used it for is we immerse it in some cell growth medium. Then we soak it in primary canine chondrocytes, which is a fancy way of saying dog cartilage cells. What happens after a few days is that entire fabric is completely coated with this thick layer of biological material. The cells love this stuff. Now, there's a lot of concern amongst our field about how safe these nanomaterials are because they're very, very small. They can get directly into your lungs if you breathe them in. And nanotubes in particular have this annoying quality of being very, very long and very, very sharp, a quality they share with crystals of asbestos. So it remains to be seen how safe these materials are. But actually, at the cellular level, our bodies kind of interpret these materials as an element of ourselves. In fact, if we look at the chemistry of what's going on in these cells, they believe they're growing on bone. So there is a potential here, real potential, for being able to insert little meshes like this to regenerate arthritic joints. And given how strong these nanotube fibres are, they'll probably be better than they started off as well. So this is a scaffold. This is a way of telling individual cells how to build themselves back up into tissue. That's great, fantastic. So let's talk, moving on, nanowires. These are our other kinds of one-dimensional materials. Now these are grown as well, much like nanotubes are, but they're not grown in a furnace at 1,000 degrees. They're grown in solution, using precisely the same chemistry which was developed over 100 years ago, used in photographic film. What we do is take a salt of silver and we cause it to turn back into silver, metallic silver. If we do that in a very controlled way, we get this beautiful swirly ink. And if we zoom right in on that ink with our electron microscope, we find these tiny little filaments of silver metal. Now these have some very neat properties from an applications perspective, and I'm an applications sort of person. Just like graphene, they're very, very conductive. They're actually more conductive than graphene because these wires are made of silver, so they're as conductive as silver. They're also, whoa boy, they are also almost completely invisible. They're very, very transparent because they're so thin. They don't really interact with light. And the processing, how we can use these to make things is really, really simple. Because they're in liquid, I showed you a bottle of the ink, we can paint them, we can spray coat them, we can do all sorts of things. All at room temperature, all using very nice, friendly solvents like water. So one thing that we can use this for, why is that not hidden? That's terrible, that's giving the game away, is we can make touchscreens with them. So, touchscreen in your phone, touchscreen in my phone, is a sheet of a very, very brittle material called indium tin oxide, supported on a layer of glass. And it's the glass that breaks when you drop your phone. And I'm not going to demonstrate. But we can make these sensors just as easily with silver nanowires. We can spray them down onto a piece of glass, just like this. We can use a laser to pattern that sensor so that it has the ability to detect where our fingers touch it, how many land on the surface. And these work very, very well. They work as well as any commercial phone touch sensor does. But they have a little problem. Silver nanowires are eye-wateringly expensive. Silver is quite expensive, about $1,000 per kilogram. Silver nanowires are a factor of 1,000 more expensive than that. They're about $1,000 per gram. So this isn't a great way of making large quantities of things. So what we found that we can do, and you saw this image earlier, is we can add tiny quantities of graphene to replace some of the silver. We put down less silver, we put our graphene film on top, and this produces something which is more conductive than either material on their own. And this is a very clever trick, which we discovered completely by accident. Now, what's the advantage of doing that over this? This is quite cheap, this hybrid material of silver nanowires and graphene. It's competitive with the materials used in our phones at the moment. But what can that do that this can't? Given the game away already, but we can put it on flexible things, which you can't do with ITO, which is what's used in your phone at the moment. We can spray these on plastic, and hopefully now, Fantastic, it at least plays at the right point. This is a sensor produced in our lab, which does precisely that. It is a bendy smartphone screen, touch sensor. And these are unbreakable in the same way that shatterproof rulers are. This screen is made from that same plastic. So it's very, very tough, can absorb a lot of impact energy. And ultimately what this is pushing towards is that bendy, rolly, foldable smartphone that you absolutely never knew you wanted. And as if by perfect serendipity, yesterday, Samsung announced a foldable tablet computer, just as if to prove me perfectly right on the night, which you'll be able to buy apparently in a couple of months' time if you've got £1,500 to spare. So maybe not just yet. So that's nanowires. That's our 2D sheets, our 1D rods. Let's do our 0D dots. And the first dot I'm going to talk about is these little beauties. We saw these up on our map earlier. Now these molecules are tiny little cages of carbon atoms, and they were discovered, co-discovered, by Professor Sir Harry Kroto while he worked here at Sussex. This discovery, it took him and the team of people he was working with quite a long time to work out that these 60 atoms were arranged in a ball, but it did win them the 1996 Nobel Prize in Chemistry, so it's not all bad. You may recognize this structure of tiled hexagons and pentagons as exactly the same shape as a football, where you have these intersection points, which is where the carbon atoms sit, and then the bonds between those atoms run along the stitching. This molecule, particular type of molecule, is named Buckminster fullerene, which is a hell of a mouthful. It's named so because the structure reminded Harry and his co-workers about these geodesic dome structures designed by the architect Buckminster Fuller, hence the name. Now, these materials, these molecules, are found in a shockingly diverse number of places, from candle soot, which you can make at home. There's not much in there, but you can make it at home, all the way to dust clouds in the deepest, darkest reaches of space. These materials seem to be almost everywhere in our universe. They've been recently discovered in coal deposits, so they grow under the ground as well. They are very, very stable, beautiful, perfectly symmetrical cages of carbon, 60 atoms apiece. But there are other kinds of dots. Just as we had carbon nanotubes made of carbon, we can have metal quantum dots in a similar vein to the silver nanowires. Here's an example. These are gold quantum dots, about 60 nanometers across. And these are grown using exactly the same chemistry that silver nanowires are. We dissolve a salt, we turn it back into the metal, forms these tiny little particles, but these just don't grow into sticks. Now this is not a new technology by any stretch. People for centuries have been adding gold salts into molten glass. What happens when you do that is you get those nanoparticles, but you get them embedded in the glass, and that gives stained glass this beautiful, rich color, which doesn't bleach over hundreds and hundreds of years. This one, admittedly, is only 19th century, only. But this particular practice dates all the way back to 4th century Rome. This cup has gold nanoparticles in it, and you can tell because when you light it from the front, it looks green. It looks like sort of fairly poor quality green glass, but if you light it from behind, it glows red. This is one of the interesting properties of materials this size, that the way they interact with light is not defined by what they're made of as much as it is how big they are. So there is another intriguing property of gold quantum dots, and that is if you shine a UV light on them, they glow. And the color that they glow depends on how big they are, not what they're made of. Now this is very cool technology, and you can buy this in the form of QLED TVs, quantum dot LEDs. Now, what's actually going on in there? Where are those quantum dots? They hide behind the display in the form of a plastic film like this. This is precisely a sample of a material from one of these televisions. I didn't dismantle one to get it, promise. And what happens is, I have a UV light here, and hopefully this will show up nice and clearly. So if I shine this on any other surface, you just get a purple reflection. If I shine it on here, you get a beautiful yellowy green sort of colour. And the reason for this is the quantum dots in here are designed to emit light in the red and in the green region of the spectrum, at the two wavelengths where your eye has cone cells sensitive to those colours. So what happens to make white for these TVs is you put your light source behind the film, and the combination of the blue that's transmitted through and the red and the green that it produces makes a very, very gorgeous balanced white light if done properly. And all of this is in aid of putting more colours in the rainbow, as I've titled this slide. This image is a very crude representation of all of the different colours the human eye can see. And then this line around the outside are pure spectral colours. So if you have a laser at any given wavelength, the colour it appears to the eye will fall on that line. Now most displays, modern displays, don't fill that whole area, which means that we actually can't produce on a television the rich variety of colours that actually exist out in the world. But by using quantum dots in our LED TVs, we can enhance that range. We can produce more colours, which gives these displays a sort of a depth of colour and a range that you just can't get any other way. And they're cheaper than doing it in several other ways as well, despite being made of gold. So that's one use for gold quantum dots. We're going to finish, actually, almost at the end here, on a last application. So the title here is maybe a bit aggressive, but what we're actually talking about is attaching biomolecules to the surface of these tiny little dots. What that means is they'll interact with proteins, chemicals in the body, for example. They can attach to them, and then when we shine a light on these nanoparticles, we can interact with that molecule very, very selectively. We can use this for doing detection, but we can also use it for killing tumours. So the idea behind this, and this is a process called photothermal therapy, is that you take these quantum dots tagged to attach themselves to cancer cells, inject them into your bloodstream, and they will accumulate in a tumour. Shine a very, very bright light on them at a particular wavelength that they interact with very strongly, and they get hot, really hot, and that kills the cells that they're attached to. You can see that this is a particular example from a particular paper, but the temperature rise is 30 degrees. 65 degrees, there will be basically no cells left alive after an extended period of time. And this is borne out in this particular worker's data as well, that if you use a bright enough light, you can kill almost all cancerous cells in these particular examples. So this is fantastic. This is a great use for our new nanotechnology. And with that really brings it to the end of the tour, if you like, this little guided tour of the world of really, really tiny things. I hope you've enjoyed it, I really do. And obviously, if you have any questions, I'll be more than happy to answer them. So with that, thank you for your attention. Thank you very much.